Okay, so today it's the last class, and we have a fair amount of stuff to do. So let's get to it. And I'm just going to get right into the new material. And if we have time left over at the end, then I can answer questions. Yes?
Are you going to be tomorrow here?
I will not, no. I can answer questions on email. But let me start by just saying when my office hours are during finals week and that kind of stuff. So what do we have left? First, the final, exam 5. You can take it Monday night. That's 12/12 at 6 p.m. in the room next door, so that's 1326. Or the one that's scheduled for our class, the day class, is Thursday, 12:15 at 2 p.m. in this class, 1328. So you don't have to tell me ahead of time. You can just show up for whichever one of those you want. And my office hours for next week. On Monday, it'll be from 3 to 6. Next door, where my Monday office hours always are, in the lab, 1324. And then Tuesday is in my office from 1 to 2. That's 2302. And then Wednesday, 3 to 6. Usually it's only 5 to 6 on Wednesdays, but we'll do 3 to 6 on Wednesday. Back in the lab, that's 1324. Any questions about any of this? Okay. We've been talking about rotational motion. And we're done talking about kinematics. And so now we're on to kinetics. And kinetics is when you, it still includes kinematics, but you also include the causes of the motion. With particle physics, that means forces. With rotational motion, that means moments. And you also include resistance to motion. In particle physics, that means mass. In this, it means moment of inertia. And remember that for particles, the main result of kinetics was Newton's second law. And it said F net is equal to the mass of the chosen object times the acceleration. The F net is what you get if you add up all the individual forces acting. In rotational kinetics, we're heading towards a similar thing. So the main result is the rotational version of Newton's second law. And it looks like this. If you add up all the moments, so I'll write that as the net moment about this axis A, that's equal to the moment of inertia about A times the angular acceleration. We already know what angular acceleration is, but we haven't defined the moment about an axis or the moment of inertia about an axis. So before I can talk about using this equation, I have to define those two things. So I need to define the moment of inertia, the moment about an axis. Let me just write that as the moment about an axis, no net. And the mass moment of inertia. Okay, let's do, yes. Let's do the mass moment of inertia first. It's the easy one. It's like a good warm-up. So the mass moment of inertia about an axis. So this is a measure of how hard it is to get an object spinning. An example of this is if you watch gymnastics, there's a few ways you can do flips, but here's one of them. Okay, so this guy's doing a backflip like this, and here's another one. So say you do a double flip. Which one of these do you get more points for?
The right one.
You get more points for doing a double flip like this than you do like this, because it's hard to get your body rotated when you're stretched out, laid out like that. When you're tucked up tight like this, it's a lot easier to get it rotating. So doing the same trick this way is harder. And this way is easier. And so this harder way is a higher value of the mass moment of inertia. And the easier way is a lower value of the mass moment of inertia. And what the mass moment of inertia depends on is, so IA measures how far mass is distributed from the axis, or mass is positioned from the axis of rotation. And so if you look at this, I mean, I don't know how much like a foot weighs or a head weighs, but I don't know, say a foot weighs, your feet weigh a pound, your head weighs 10 pounds, something like that. The axis of rotation, just flying through the air like this, is at the center of mass of the body. So your 10-pound head is half a meter away from the center of the axis of rotation. Okay? And your 1-pound pair of feet are positioned half a meter, maybe a little more away from the axis of rotation. Definitely a little more, unless you're a hobbit. Yes?
Okay, so like down to your example yesterday, that the easier one would be like the point closer to the axis, and the harder one, like a piece of wood, you got like the 2 points on it, and then you're saying it's one place further out.
Oh, yeah, that's right. Yep, that's right. And so with this one, you have mass distributed pretty far from the axis of rotation. With this one, the whole point of getting in this position is to get every bit of mass as close as possible to the center of mass, the axis of rotation. And so this is a lot easier to get spinning. Shoot, I forgot to bring this demo in. Let me go get it. It's worth it. We're going to do these calculations for rectangles, just for rectangles. We'll do calculations for rectangular shapes. So let's say that you have an object with a length L and a height W for width. And let's say the mass is m. If the axis is right at the center, then the mass moment of inertia rotating around the center is equal to 1/12 times the mass times the quantity length squared plus width squared.
Could you move up just a tad?
Mhm.
Thank you.
And so, like, for example, if you have a rectangle, it doesn't matter what orientation it's in, that has a length of 1 meter, and a width of 0.5 meter, and a mass of 10 kilograms, and the axis of rotation is right at the center, then the mass moment of inertia, the measure of how hard this thing is to spin, is 1/12 times the mass times the quantity 1 squared plus 0.5 squared. And that is 1.25, 125 divided by 12. Can someone divide, what's that, 10.4? Oh, yeah, 1.04. Yep. So 1.04. And what are the units? Kilograms? Kilogram meter squared. Yep, good. So kilogram meter squared. You can see that from the formula. You have meters squared for the length, for these lengths squared, multiplied by kilograms. And so the units for mass moment of inertia are units of mass times length squared. That always has to be the case. And then if you're in SI units, it's always kilogram meter squared. Okay, so if you're rotating a rectangle about an axis at its center, this is how you do that calculation. But what if it's not rotating around the center? You could, like, imagine taking this rectangular shape and bolting it to the wall, and, you know, like it can rotate around the bolt. You could put that bolt anywhere in that rectangle you want. And wherever that bolt is, you need to calculate the moment of inertia around that point. So what if that bolt isn't in the center? So what if the axis isn't at the center? Then you use what's called the parallel axis theorem. And the parallel axis theorem says the moment of inertia about some point A is equal to the moment of inertia about the center plus the mass of the object times d squared. I'll tell you what d is. It is a distance where d is the distance from the center to the axis. Okay, so let's say we have this rectangle. I guess I'm going to use the same length. So this is 1 meter. The width is 1/2 meter. And the mass is 10 kilograms. And let's calculate the moment of inertia about A in the center, B at the end, and C at the corner. So the moment of inertia about A, moment of inertia about B, and about C. For part A, if the axis is at A, that's at the center of the rectangle. So that's 1/12 times the mass times the length squared plus the width squared. And you get a value of 1.04 kilogram meters squared. Okay, so now if the axis isn't at A, if instead it's at B, then to calculate the moment of inertia at B, well, first, what do you think? Is it going to be easier or harder to, like, imagine this being, don't think of it on the wall because then gravity messes with it. Think of, we're looking down at this, and these are axes of rotation connecting it to the ground. So first, say you can spin it around this point here. Second, say there's like a hinge here, and you can spin the whole thing around that. Is that going to be easier to get spinning or harder to get spinning, do you think? Harder. And you can actually see that mathematically if you look at this parallel axis theorem rule. What it says is the moment of inertia about any axis that's not the center is the center plus this other thing that can only be positive. mass can only be positive, and anything squared can only be positive. So the smallest moment of inertia for any body is when the axis is at the center. All right, so moment of inertia about B is equal to the moment of inertia about the center plus the mass times the distance squared, where that distance is from the center to the axis. So what's the distance I want here? 0.5, yep. And so that's 1.04 plus 2.5. And so that is 3.54. And then the last one, the moment of inertia about C. So this is the moment of inertia about the center plus the mass times a distance squared. And let's think about what that distance is here. So here's the rectangle. We're looking for this distance. Okay? And if you set it up as a right triangle, you can use the Pythagorean theorem. What's the distance of this? What's the length of this vertical leg? 0.5. What's the length of the horizontal leg? 0.25. And so the distance squared is equal to 0.5 squared plus 0.25 squared, which is, what's that, 0.375? No. 3125? 3125. So the moment of inertia about C then is 1.04 plus 10 times 0.3125. That's already D squared, so I don't have to square it again. And that is 4.165 kilogram meter squared. Okay, so in which of these positions would it be hardest to get this rotating? Which of these three axes would make it hardest to get this rotating? C. It had the biggest moment of inertia, so it's hardest to get it rotating here. Okay, so that's all we need to know about mass moment of inertia. Now we have to talk about moments. So the moment, or another word for the moment, is torque. About an axis. If you've used a torque wrench or something, that's what it's measuring, is what we're going to talk about calculating now. Okay, so say you have some body. You have some body. That was stupid. Okay. Let's say this is the axis. And at some point P, there's a force applied. And so let's draw a line between the axis and this point P. And let's say that the force that's applied at P is perpendicular to that line. That's a pretty strict requirement. There's no reason to believe that if you apply some random force to an object and its axis is here, that the force is going to be perpendicular to that line, right? That's asking a lot. We'll figure out how to deal with it in a second if that's not the case. But for now, we're going to assume that the force is perpendicular to this line. So this is a right angle. Then the absolute value of the moment about that axis is equal to the force times the distance d, where d is the distance from the axis to that point P, the point where the force is applied. Okay, so this here is the distance d. So that gives us the magnitude of the moment, but it doesn't give us the moment because it doesn't tell us what the sign is. So now to get the sign, to get that you have to think, what direction would this force cause the object to rotate? So what direction would that force make the object rotate? If it's counterclockwise, then the moment is positive. If it's clockwise, then the moment is negative. It's just like the angles with sine and cosine. A counterclockwise angle is positive and a clockwise angle is negative. Intuitively, here is how to think about a moment. Okay, so say you have a bolt that's stuck, it's hard to turn, and you're trying to turn it with this wrench. Let me try to make this a little more level. Okay, so let's think about 3 locations. So say that there's some fixed amount of force that you're capable of applying to this wrench. Where are you going to get the best effect? Are you going to get the best effect by applying, say, 100 newtons of force straight down above the bolt? Or halfway out on the wrench? Or all the way out on the wrench? All the way. And so this idea that you cause more tendency to rotation by exerting your force a long way away from the axis is what that measurement of a moment tells you. Okay. If you apply the force straight down on a line through the middle of the bolt, no matter how much force you apply, that's never going to turn, right? All you're going to do is eventually just rip the head off of that bolt. Yep.
I don't know if this is how this works, but would that be kind of like in baseball, where if you hit the ball with like the middle of the bat, it's not going to go as far as if it hits it towards the end, or is that?
You know, that is because of the speed of those points. And so if you think about, that's really more connected to the equation that says speed is equal to angular velocity times the radius.
Okay.
And so the bigger that radius is, the faster that point on the bat is going.
Is that the same as like hitting a nail with a hammer? If you hold it at the...
That's the same as this. So if say you're applying some fixed amount of angular velocity to this hammer, if you hold it at the end and create that angular velocity, the head of the hammer is moving a lot faster than the head if it's only 4 inches away from your hand or something. So those have to do with the speed.
So you're saying that as long as it's in contact, then that will be true statement.
As long as what?
Two object is in contact. Like it doesn't have to be a torch and like how the wrench is already touching the bolt.
Yes, right. So I guess really what's happening here, the way to think about it is if I drew a free body diagram of the wrench, that bolt would be applying a torque one way to keep the wrench from turning, and this force would be applying an opposite torque to try to make it turn. Okay. So let's do an example. So let's say that there's a circular object, and let's put the axis over at the edge. And let's say that there's a force applied at the center this way. Let's say the force is 10 newtons, and the radius of this circle is 0.2 meters. What's the moment about that axis applied by that 10 Newton force? The first thing you have to do is figure out whether the conditions are met for us to use our calculation. So we have to check and make sure that the line between the axis and the point where you're applying the force is perpendicular to the force. So draw this line. Are those two perpendicular? Yeah. So the first thing is the force is perpendicular to the line between the axis and the point. So we can do the calculation. And so now we know that the absolute value of the moment is equal to the magnitude of the force, that's 10 newtons, times the distance between the axis and where the force is applied. What's that distance? 0.2, yep. And so you get an absolute value of the moment of 2 Newton meters. And now we have to think about the sign. Question?
On the card before it, about like, because earlier you said like the gymnast or whatever.
Uh-huh.
But, and you said like she's like
Laid out, yeah.
tucked in, then like that was more better.
Yeah, tucked is easier. It's a lower moment of inertia.
Okay. So then, you're saying like, okay, so for like the wrench problem,
Uh-huh.
it would be like better and then worse. So
Well, okay, so in the wrench problem, this axis doesn't move. So no matter what the axis of rotation is the middle of the bolt. Okay, it's rotating around that bolt no matter where you hold on to it. And these things are just determining where that force is applied. Okay, so now we have to think about the direction of this rotation. Question?
Sorry, so what concept is being applied if the radius was smaller, if it was a smaller circle, so if it was like 0.1 meters instead of 0.2,
Yep.
what concept is that then? Where the, what's the word? Where the absolute is going to be more than when the radius is smaller? Because it's going to be,
No, it's going to be smaller because you're just moving that force closer to the axis. It's like getting closer to the bolt and applying the force to the wrench.
Okay.
Okay, so now think of this thing. When it rotates around that axis. So this whole circle goes around like this. Which way, if you applied this force of 10 newtons, like imagine imagine there's a little pin here and you can tap with a hammer to get this moving. Is this going to rotate clockwise or counterclockwise? It's going to rotate clockwise this way, and so that's going to be negative.
How did you determine
So when this thing rotates, it starts in this position, and then it goes to this position, and then this position, and then this position. Okay? And we're trying to figure out which way it would go around this circle if you applied a force up. Would it go from here to here to here to here? That would be counterclockwise. Or would it go from here to here to here to here? And so it's clockwise, and that means that the moment is negative. So it's a clockwise rotation. So the moment about the axis is negative 2 Newton meters. Any other questions about that one? Okay, so now we've, oh no, I'm not done with that actually. There's one more thing we have to talk about. So what if that force vector is not perpendicular to the line between the axis and the point where the force is applied? It's very likely, much more likely, that they won't be perpendicular than that they will. So yeah, we'll have a way to sort of modify this so we can use it. So what if the force is not perpendicular to the line between the axis and that point P? Well, it turns out without changing the problem, you can move the force around on the body as long as you do it in a specific way. So without changing the problem, you can move the force anywhere along its what's called line of action. So, for example, if this is the body and the force really is physically applied here, without changing the problem, you can move that force to anywhere along this dotted line. It doesn't even matter if it's actually physically on the body. Mathematically, it works the same as where the force is really applied. So this is the line of action. It's parallel to the force, and it goes through the point where the force is physically applied. Mm-hmm. It doesn't have to touch the object. It's just, this is a mathematical thing that we're going to use. It's not an actual physical thing. It's not like you're really moving where the force is applied. It's just a mathematical treatment. But what this does is it lets us move the force mathematically to a place where the force is going to be perpendicular to that line. Okay?
So in the circle,
Mm-hmm.
let's say,
The example right before?
yeah,
This one?
let's say if it was on the point 2 pointing out, how would you do that?
If it was here,
Yeah.
pointing up. So its line of action would be through that point, parallel to the force.
Yeah.
So you could move the force location from here up until the line between the point is perpendicular to the force.
But when you change the distance, though?
It changes the distance. Yeah, it does. It does. But it works. So the idea is that you move the force along its line of action until the force is perpendicular to the line between the axis and P. And then you do the problem as if that was the original location for the force. Do it as if that's where the force really occurred. Okay, so.
So what question is with the circle? So does the distance change? Does
Mhm.
it give us the distance change? Or how would we figure out that the distance?
The trigonometry on that would be a little complicated. I wouldn't give you one like that. I'll give you an example that'll be more like the kind of things you'll have to do.
Okay.
But yeah, you could use trigonometry to do it. It just isn't really, I'm not really concerned about whether you can do that calculation. So okay, here's an example problem. So let's say the body is this. And the axis is the center. And let's say a horizontal force of 20 newtons is applied at this corner. Say this distance is 1 meter, and this distance is 2 meters. What's the moment applied about that axis? All right, well, first, if you draw a line between the axis and where the force is applied, you can see it's not perpendicular to the force. So we can't do this problem by measuring this distance. Okay? So what we have to do is we have to find the line of action of this force, and it's like this. So we can move that point P, the location of that force, anywhere we want along that line of action. And we have to move it to a place where the force is perpendicular to the line between the axis and where the force is. So where along this line of action should I move that force to? Right above, yep. So you can think of this as like the new problem. Now the axis is here. The force is applied here. If you draw a line from the axis to where the force is applied, these are perpendicular. And so now the absolute value of the moment about that axis is equal to 20 times what's the length of this dotted line? What's the distance from the axis to P? 0.5. And so the absolute value is 10 Newton meters. And now if this was free to rotate around this axis, and you applied a force at this point, that direction, would this thing spin clockwise or counterclockwise? Clockwise. Anybody have any questions about that? And since
If you're looking for clockwise or counterclockwise, do you always push up or not?
no, you push the direction the force is going.
Okay.
Yep, so in this case, you're imagining pushing the top of this thing this way, and it's going to make it spin like that.
Okay.
So since it's clockwise, the moment about the axis is negative 10 Newton meters. Any other questions about that one? Okay, so now finally we're ready to do the rotational Newton's second law. I'm going to call that Rn2L. It looks very similar to Newton's second law, and actually it's completely derivable. Just it's a mathematical thing that you can derive from Newton's second law. And what it says is if you add up all the moments about the axis, that has to be equal to the moment of inertia about that axis times the angular acceleration. Okay, so I'm going to do two examples that are similar, but I think they'll kind of show how this all works. So let's say there's a board. And it has an axis in the middle. And there's a 10 Newton force applied down on the left, and a 5 Newton force applied up on the right. And let's say that this is connected to the wall by this axis, which means gravity is acting down on this object. Let's say this distance is 1/2 meter. This distance is 1/2 meter. And this is 0.1 meters. And let's say the mass is 2 kilograms. And we want to calculate the angular acceleration. Okay, so the first thing I'm going to do is draw a free body diagram. We have a downward force of 10, an upward force of 5, and then we also have the weight. With particles, it didn't matter where we put the weight because everything was assumed to happen at the same point. Now it does matter, and so when we apply the weight, we have to put it at the center of the body always. So the weight is 2 times 9.81 acting at the center, so 19.62. Notice the weight always acts at the center. So let's first calculate the moment of inertia. Yes, it's always at the center. And so we'll see how that works in the next example. I'll put the axis somewhere else. So the moment of inertia is equal to 1/12 times the mass times the length squared plus the width squared, and you get a value of 0.1683 repeating kilogram meter squared. And now we have to calculate the moments due to each of these forces, and we're going to add them up. So let's first do the moment produced by the 10 Newton force. If we treat this force like it's acting at the corner here, then the distance from the axis to that point isn't quite perpendicular to the force vector. So we have to move that force vector along its line of action. So here's the line of action of that force. Here's the axis. We want to move it to here. And now that force vector is perpendicular to this line, so we can use the equations. The absolute value of the moment is equal to the force times the distance between the axis and where it's applied. What's that distance? 0.5. So that's 5 Newton meters. And would this force make this thing rotate counterclockwise or clockwise? Counter, yep. And so the total moment, or the moment with the sign attached, is positive 5 Newton meters. Okay, now let's do the same thing with the weight. Here's the axis. The weight is actually occurring at the axis. And so when that happens, it's like trying to turn the screw by applying a force directly to the bolt. It's not ever going to turn it. It doesn't cause any kind of rotation at all. You can think of that distance d as being equal to 0. And so the absolute value of the moment produced by the weight is equal to 19.62 times 0, which is 0. So MA is 0. And then the last one is that 5 Newton force. The 5 Newton force has a line of action like this. Here's the axis. And so we need to move it to here. Then the force of 5 newtons is perpendicular to the line between the axis and where it's applied. So the absolute value of the moment is equal to 5 times, what's the distance between the axis and that point? 0.5. So you get an absolute value of 2.5 Newton meters. And then would that force, if this is what it rotates around, would applying a force here make it rotate counterclockwise or clockwise? Counter. And so that moment is positive again. So MA is equal to positive 2.5 Newton meters.
And weight will be the same.
What?
Weight will be the same.
The weight we did right above, and that didn't produce any moment because there's no distance between where it acts and the axis of rotation. Yep.
Then, do you have to, like, in every one of those, like, parts to calculating the moments, do you have to do, like, instead of the absolute value, because, like, you do the absolute value of m-axis equals, like, 10, 5 equal. Do you have to, like, rewrite it and say, like, just ma equals positive or negative?
No, I don't really care how you do the bookkeeping. I'm just trying to make it clear for when you follow the notes later. But yeah, that's right. You don't have to write out all these steps or anything. Okay, and so what we figured out is that the net moment about that axis is equal to positive 5 plus 0 plus 2.5. And we get a net moment of positive 7.5 Newton meters. And so now finally we can go to the rotational Newton's second law. the net moment, 7.5, is equal to the moment of inertia, 0.1683 repeating, times alpha. Solve for alpha, and you get 44.55 radians per second squared. Okay, so is the angular acceleration clockwise or counterclockwise? Counterclockwise because this is positive. Do we know anything about the angular velocity? Which way is it rotating? Does this tell us? So I think probably the way that you would think, what you would picture happening is that this thing is starting at rest, and you apply those forces and make it, and so those accelerations make it start to pick up speed counterclockwise. But just remember that rotational Newton's second law doesn't actually mention angular velocity at all. So what could be happening here, we don't know what the angular velocity is when these forces are applied. It could be that this thing was spinning really fast clockwise at the instant these forces were applied. And in that case, that angular acceleration would just make it slow down. You know, it could still be spinning this way. So just remember that what we're measuring is angular acceleration. It doesn't tell us anything about angular velocity. To go from angular acceleration to angular velocity, you have to use the kind of equations that we did in rotational kinematics. Okay, let me do one more example with that same board where the axis is somewhere else. So let's say it's the same board, but now the axis is at the left end. So here's the axis. You have a downward force of 10 newtons. You have the weight, and then you have an upward force of 5 newtons. So in the example before, the weight was acting at the axis, right? The weight always acts at the center, so it was acting at the axis, and the weight didn't do anything to make this thing rotate. But you can imagine, like, if you had a heavy rectangular board and it was connected to the wall by a hinge at this end, its weight is going to make it want to swing down, right? So in this case, we're going to see that that the weight actually does produce a moment that's going to try to make it accelerate that way. Okay? Yes?
So any force that's acting on the axis is not going to be
0 moment. Yep, that's right. Because the distance is 0, you know, from the force to the axis. Okay, so first let's figure out the moment of inertia. So it's going to be equal to the moment of inertia about the center plus md squared, since this time the axis isn't at the center. So we get 0.1683 repeating plus the mass of 2 kilograms times what's the distance between the center and the axis? 0.5, yep. So 0.5 squared. And if you add that all together, you get a moment of inertia of 0.6683 3 repeating kilogram meters squared. Okay, so now we have to think about the moments. Here's a free body diagram. I'm going to treat it like these forces are just along the center, just to save a couple minutes, but I'm just moving the forces along their line of action until everything that we need is perpendicular. So here's the axis. We have a downward force of 10. In the middle, we have a downward force of 2 times 9.81, so 19.62. And then at this end, we have an upward force of 5. And we're going to do the same thing we did before, just one by one calculate the moments due to each one of these individual forces. So the 10 Newton force, what's the moment produced by that force? 0, because it's acting at the axis. Now the weight. The absolute value is the force, 19.62, times the distance from the axis to the force. What's that distance? It's just from, it's not the whole length of the thing, it's just from here to here, so it's 0.5. So 9.81. And then if that was the only force acting, and this is the axis, would this force make it rotate counterclockwise or clockwise? Clockwise, right. So it's going to, this is the axis, so if you applied a force like that, it would make it swing around like this. You see that? And so it's negative.
Wait, which one are you saying? Are you just talking about?
We're doing the weight right now.
Okay.
So we're ignoring these other two and just thinking about the weight.
Okay.
So if you applied a force like this, it would make it rotate, the beam rotate around like that, clockwise, so the moment's negative. So MA is equal to negative 9.81. And now the 5 Newton force. The absolute value is 5 times the distance from this force to the axis. What's that distance? That's the full meter. So the absolute value of the moment is 5 Newton meters. And if that 5 was the only force acting, and this is the axis, would this make it rotate clockwise or counterclockwise? Counterclockwise. You apply a force this way, like imagine tapping that with a hammer, it'll rotate like this. Counterclockwise. So MA is equal to positive 5 Newton meters. Add all of those up. And the net moment is equal to 0 minus 9.81 plus 5. And so you get negative 4.81 Newton meters. And so the rotational Newton's second law says the net moment, negative 4.81, is equal to the moment of inertia, 0.6683 repeating, times alpha. And so alpha is equal to negative 7.20 radians per second squared. So what we saw is the exact same setup, except the axis moved to a new location. We got opposite directions of angular acceleration. And it just had to do with how those forces interacted with where the axis was. Like, for example, in the first case, the weight didn't do anything to rotate the body. In the second case, the weight had a big effect on rotating the body.
And did you just use the 0.6683 repeating from the first part of the problem?
We did that before I started doing moments.
Okay.
We had to, here it is right here. We had to use the parallel axis theorem. So we had the original one plus the mass times the distance squared.
Okay.
Any other questions? Yeah, it's going to be everything we've done. And so you need to go through the practice problems in rotational kinematics and rotational kinetics. But then everything before can be on it too. There will definitely be some rotational stuff, and then I'll pick and choose stuff randomly, sort of throughout the semester. Okay. Yeah. Thanks for taking my class. Bye.